Hello everyone, welcome to 9th lecture of this introduction to remote sensing course. In this lecture we are going to discuss in detail the salient characteristics of various satellites, and the most popular one, the Landsat IRS, our own Indian remote sensing satellite, also Indian remote sensing satellite Cartosat and Resourcesat, and their sensors as well. This focus of this lecture is going to be on the sensors of these satellites. Many of the slides which you might see, which you might have already seen in previous lectures, but here the emphasis is little different. First of all, as you know that we have already discussed that there are various types of orbits exist, and that is why the whole space near Earth is cluttered with several satellites. And but the two main orbits which we would like to focus, which are useful from remote sensing point of view, one is the sun synchronous or near polar or polar orbiting satellites. Most of Earth resources satellite like Landsat, IRS, Cartosat, Resourcesat, all of them are in these orbits, polar orbiting orbits. Whereas another orbit, which is another very popular one, is mainly it was for the communication satellites, which is a geostationary orbit, and this orbit is having many satellites of the world focusing for their own countries. India too is having our own satellites, INSAT series of satellites. Also one we had in the name of Kalpana Chawla, the Kalpana satellite. There are some other satellites which the data can also be acquired if they are covering the Indian subcontinent, like Meteosat and others. Since the purpose of these satellites, the geostationary one especially, is for monitoring weather and other things, but nowadays advanced sensors have also been installed on these satellites. So every half an hour or 15 minutes one can grab an image or capture a snapshot, and these many times becomes very useful. One of the examples from geostationary satellites applications in natural disaster is nowadays like for monitoring some storms or cyclones, and you might remember that a few years back there were a cyclone Hudud, but because of our better monitoring through geostationary satellites in a more or less continuous fashion, we could evacuate lakhs of people from the affected areas, and lives of several thousand people could be saved. So remote sensing has played a major role for such kind of natural disasters, and making life much safer for all of us. So two main orbits, one is a sun synchronous orbit, another one is geostationary orbit, and whereas GPS or navigation satellites, many of them are in geosynchronous orbits. But nowadays in case of GPS, several combinations of different types of satellites or different types of orbits are being used. And for example, in case of NAVIC, we don't have totally all satellites are on geosynchronous, some are geostationary and so on. So there are various types of orbits are available, their distances and other things are altogether different. For example, polar orbiting satellites are the nearest to the Earth, somewhere around 850 kilometer away from the Earth, with the plus minus 10 kilometer in range. So a complete envelope around the Earth, which is having hundreds of such satellites of various countries, including of India, are there. Then the another popular one is the geostationary, which is having about 36,000 kilometer distance, but the purpose of these satellites to focus on a small part of Earth, and since they move along with the rotation of the Earth, so they relatively we call them as geostationary satellites. So, but if we bring the GPS satellites, typical this American Navistar GPS systems, they are having the satellites in different orbits, 6 orbits, and all these the distance is about 20,200 kilometers. So Satellites are, various satellites are there. The sky is completely cluttered with the satellite, or space is full of satellite, but at different distances in different orbits. So there are hardly any chance of colliding them. So now we come to this mainly we will focusing mainly on the geostationary satellites, which covers a small part of the earth, and not like geostationary satellite, these polar orbiting satellites and sun synchronous satellites, and this is what we call as the footprint of the satellite. The red one is showing the orbit of these polar orbiting satellites. As said in earlier lectures, that the real beginning of civilian remote sensing started with the Landsat, especially the Landsat 1, which earlier we used to call as ERTS 1, which was launched in July 1972, and since then continuously we are having series of these Landsat. Currently is the Landsat 8, which is also called OLI series, launched in February 13. Still it is operational. It is providing enormous amount of data from all parts of the globe, and most importantly, data is available free of cost for any part of the globe on really in near real time. Once the data is acquired by the Landsat earth stations, which are spread over world over, within few minutes you get the data on net, and you can download and see what exactly 15 minutes back the situation was in a part of the earth where the satellite was orbiting. So that is the biggest advantage of having a complete series. Another point which I want to bring here, that since 1972 to 2016, all this data, the archives of all such data is also available. So this about 45 years of archive of such data sets, enormous data sets, has made possible for us to look for time series data analysis, especially focusing on global climate change or any long term studies, whether it is related with natural disaster, land subsidence, or many monitoring of things like whether vegetation is changing, or whether the sea surface is changing, whether the snow or snow and ice is disappearing from the ice caps or mountains. All these things, all such type of studies are now possible because of availability of all these archive data is still free of cost. As we have also seen this slide, but I wanted to bring it again, because we are now focusing not much on the satellite but on the sensors, the sensor characteristics. So this Landsat one is had this one return beam Videocon RBB sensor, which was there, but it has a altogether different technology of acquiring data. So it was not as that popular as Landsat MSS, which is multispectral scanner. The data was provided roughly at 80 meter resolution, but it was not a perfect square. As you know that a pixel of an image has to have a square in shape, but initially when we started, because of this 57 and 79 meter spatial resolution, because of some overlap of the data or the pixel with another, we had some problems, and that time we used to call as a mixel, but those problems were solved in subsequent Landsat missions, and the data sets which was available initially by MSS became very popular and very useful. So though we write 80 meter spatial resolution or ground resolution, but in fact it is 57 by 79, because here we are having a 15 meter, roughly 15 meter overlap in this. It has 4 channels, starting from initially the names of these bands were 4, 1, 2, 3, 4. Later on these were named to 4, 5, 6 and 7. Starting, we do not have any channel in the blue part of EM spectrum, as you know that a lot of this solar radiation is absorbed by the atmosphere of this part of EM spectrum. Therefore, we do not have any channel in that or any band there, but we start with visible green channel, visible red channel, visible near infrared, and there were two channels near infrared channel, 0.7 to 0.8 micrometer, 0.8 to 1.1 micrometer. And these were this sensor became very popular, and in fact the modern day remote sensing revolution started with the Landsat MSS. The latest one, and it has gone through the Landsat TM, Landsat ETM, Landsat ETM plus. Now we are having Landsat 8, which is also called OLI series, that means operational land imager, which is having data at different spatial resolutions, and many channels, 9 channels data is available. So instead of now 4 as we had in case of MSS, now we are having 9 channel data, and the channel 8 is having 15 meters spatial resolution, which is specially designed for panchromatic data acquisition, whereas channel 1 to 7 or bands 1 to 7 and band 9 are having 30 meter spatial resolution. So nowadays, because the technology has compared to Landsat MSS till in 2016, the technology has improved so much that on the same satellite we can have sensors which can acquire data for various bands, but at different spatial resolution. Earlier these things were not possible, and especially these TIRS thermal infrared bands are channel 10 and 11, and which are collecting data at 100 meters, but later on they are resampled to 13 meters so that we can use them along with our multispectral data. So this kind of data, you think that earlier we had only 4 channels data, now 11 channels data, 2 channels in thermal channel. In case of MSS, we did not have any thermal channel. So lot of data is now available. Thermal channels, applications of thermal channels is also very useful. For example, like for sea surface temperature mapping, extensively thermal channels are being used, and also for land surface temperature mapping, and then time series data analysis, how things changes in thermal regime of the surface of the earth. This is only possible if we are having thermal channels. So in Landsat we are having thermal channels, in a Aster satellite we are having in thermal channel, and of course in NOAA, though the data is available at 1.1 kilometer resolution, but having wide swath, large coverage, but it is also having 2 thermal channels, which we will see later. Most importantly here, that we are comparing the just previous Landsat 7 and 8 satellites, that how things keep changing as new sensors are designed and so on. As you can see that the top one are the OLI, that means the Landsat 8 bands which are located, and in the background what you are seeing this spectra which is showing the absorptions or atmospheric windows. So you see that very carefully these have been designed to place there, so that these the shaded one are the atmospheric windows and these are the opaque area, so that we can acquire data of different ground features in all these 11 channels in case of OLI data. And whereas compared to the improvements with the lens between Landsat 7 and 8 is that the 7 had only the 7 channels, whereas 8 is having 11 channels. Though there were only 1 channel for thermal data sets, but this in Landsat 8 we are having 2 channels. Now advantage of having 2 channels in thermal range, because many of algorithms which drive the land surface temperature or sea surface temperature, they are based on split window algorithm, and that means they require 2 thermal channels to estimate the temperature of the earth. And for that purpose the OLI series, that means Landsat 8, is very suitable, because you are having 2 channels. And also if you see very carefully, you would find that all of these channels which were in the in Landsat 7, they have further improved, and these channels have become further narrow, because the advantage of having narrow channels that you can discriminate minute changes in different objects which are present on the earth very easily compared to having broad channels. So like channel 7, and you are having again you compare with Landsat 7 and Landsat 8, there is a difference. That's Landsat 8 is band 6 and Landsat 7 band 5. Again band 5 of Landsat 7 is relatively almost having double width as compared to band 6 of Landsat 8. Similarly, as you can see, the panchromatic, so instead of covering a very large area of visible part of EM spectrum, in case of Landsat 7, as you can see, Landsat the band 8 had a very broad spectrum. Now in Landsat 8, the band 8 is having almost half width there. So what we are seeing through the development of, say, just in case of Landsat series, the channels are, a number of channels are increasing, spatial resolutions are increasing for almost all channels, and the width of these channels are reducing. That means the spatial resolution is improving, our radiometric resolution is improving, means the quantization. Instead of having just 6 bits data or 7 bits data, now we are having 8 bits or 10 bits data. And also this channels are also our spectral resolution. That means the width of channel is also reducing, and that means the improvement in the spectral resolution. So on all fronts almost, except for temporal resolution, the spatial resolution is improving, the radiometric resolution is improving, and your spectral resolution is improving. Just if we compare only Landsat 7 and 8, we can see the changes, but if we compare Landsat 1 and 8, there are huge changes. Number of channels have also increased, and multi-spatial resolution data are nowadays also possible with these sensors. So just in a one Landsat series, huge changes, major changes have been observed, and maybe in future Landsats we will be seeing more better improvements on this front. Okay, so now we will compare the spatial resolutions one by one for all bands of between Landsat 7 and 8. What we find, like band 1, which we also roughly we say is a blue band, is having 30 meter spatial resolution in case of Landsat 7, but in Landsat 8 this remained same, but another band 1, so there is a change in the numbering of these bands are there, but from between band 1 to 5 not much changes in terms of spatial resolution and neither much change in their position, but definitely, as we have seen in the previous slide, that these bands in Landsat 8 has become much narrower. That means our spectral resolution is improving, we are putting more bands, more number of bands within the available atmospheric windows. And band 6, if you see here, that it was providing data at 60 meter resolution, now it is providing in Landsat at 100 meter, but these are instead of one channel, now we are having 2 thermal channels data. And in case of band 7, the spatial resolution remains same, and though there is some changes in the spectral band, Landsat 7 band 8 is having 15 meter, and that is spatially reserved for panchromatic data, whereas Landsat in case of Landsat 8 band 8 is having almost the same thing, but of course it has become further narrower. One more band has been added here after this is a band 9, which is having 30 meter, and especially it is designed to capture data about the snow or ice. So after seeing this comparison between Landsat 7 and 8, now I would like to focus mainly on Indian remote sensing satellites. As you can see, there are many, and we started with the AVHRR, Bhaskar, and now this this is continuing, and only in recently that satellite is not added here, that we are having now in only in June 2016 we had another satellite which is our Resourcesat 2. But before that I would like to again bring our focus mainly on the sensors characteristics of these satellites, but at the same time we will also try to compare the other characteristics of all these satellites, because this is not that now these satellites are not working and therefore like after 95 IRS stopped working. But the important part here, for every satellite, if that for whatever the period they have worked, the data is now available and almost free of cost on through net. Even our IRS 1A, 1C, 1D, all kinds of data is also available. So because of availability of these archives, we need to know details of all these satellites, because there are improvements, as you can see here in the IRS 1A, 1B. It lasted only for between 1988 to 95, and then 1B only after 91. So we had some overlap, and in tandem the spatial resolution was improved quite a lot, and the altitude of the satellite was little higher. Instead of 840 or 50 kilometer, we had at 904 kilometer. Generally the equator crossing is 1030, but local overpass time might be around 930 or so, and it keep moving. The temporal resolution was 22 days when you had the only one single satellite, but when you are having tandems in tandem, then this was reduced for some time between these about overlapping time for 11 days. These two satellites IRS 1A and 1B had two sensors, LIS 1 and LIS 2, and these linear sensors, we will see much more details about these. Then in the next in the series IRS 1C and 1D, again there were some overlap between 1C and 1D. This is these are not only for 3 years they worked, and then the orbits were little closer as compared to IRS 1A, 1B, and other things remain same. The repeativity, because once you are in tandem, the temporal resolution improved to about 12 days, and it has one more extra sensor. So LIS 3 we had, instead of having LIS 1 we had then panchromatic sensor and wide field of view sensor, that is the WIF. So it instead of Landsat LIS 1, LIS 2 we had LIS 3, PAN and WIFs. Then we started another P series of the satellites, IRS P, also called as Cartosat, and in between also Resourcesat. Resourcesat 1 lasted for 5 years. It was again almost the same altitude, same crossing time, and the repeatability or this temporal resolution was also same. Now in this LIS 3 sensors continue, because LIS 3 sensors was one of the best ever sensors of IRS series of satellites. Therefore it got continued in the Resourcesat. We introduced one more LIS 4 which has better spatial resolution and other characteristics, and instead of WIFs we have AVHRRs. And in Cartosat, because the purpose of this IRS P Cartosat was altogether different, therefore orbits was much lower. It was mainly for to acquire the stereo data, so that a digital elevation model using these stereo pairs acquired by the Cartosat can be developed, and which have been developed for all parts of India, and those data, that means digital elevation model, are also available free of cost for all parts of India at a very high resolution. So this was the advantage. So here we need not to focus too much on the 126 days of temporal resolution, because the purpose of this satellite was altogether different. IRS 1A, most of these details we have seen, so I am going to skip these satellites. One important point I want to bring about this descending world and ascending world. Generally in the morning hours we are having the southbound satellites, and they acquire the data, so that is why when it is coming from north to south we call as descending mode, when it goes in afternoon from south to north we called as ascending mode. So that is the only thing. Another important thing is the time it takes to complete one orbit. So roughly about 2 hours it takes to complete. Most of these sun synchronous satellites are having that much of timing is there. When we compare the sensors list 1 and list 2, as you can realize that there is a huge difference between spatial resolution of list 1 and list 2. It is almost double in that sense, though as you know that smaller the digital value or number, higher the spatial resolution. And the swath width got reduced, again it got half because coarser the spatial resolution of any sensor, larger is going to be the swath width. So there is a if this value is larger, it means spatial resolution number is larger, then swath is also going to be the larger. But the term which we will use is relatively coarser, and here is the wide swath, here is the better spatial resolution, but narrow swath is there, because as you go higher and higher in spatial resolution, the swath width reduces, the strip which is going to cover of the part of the earth becomes narrower and narrower. So the repeativity, the same repeativity can also be, get affected, but here because it remained almost same, and the number of bands, it has the same identical bands between Landsat 1 and 2. Now if we compare Landsat 3 and 4 and AVHRR, what we find that because Landsat 4, this list 4 was panchromatic, and it provided data at 5.8 meter resolution. At that time that was the one of the best data available from Indian remote sensing satellite at 5.8 meter resolution at panchromatic bands. But at the same time the same satellites like IRS 1C, 1D had list 3 sensors, and they had the higher spatial resolution compared to list 2, and that was 23.5, and also it has 4 bands, band 2, 3, 4, 5, and then AVHRR has the resolution relatively poor as compared to list 3, but the purpose was here to cover a large area, more swath. As you can see, the swath width in case of Landsat, in case of list 4 panchromatic, it was 5.8, whereas the swath width was 70 kilometer. Here in case of list 3, where the spatial resolution was 23.5 meter, swath width was 140 kilometer, and in case of AVHRR the swath width 740 kilometer. As I was mentioning, the higher the spatial resolution, lesser the swath width you will observe. This is what it is demonstrated here, 5.8, so 70 kilometer swath width, 23.5 meter spatial resolution, 140 kilometer swath width, and 56 to 70 meter spatial resolution swath width has improved, that is 740 kilometer. Another important thing is one is radiometric resolution or quantization term which we use. So one is spatial resolution, another one is radiometric resolution. So radiometric resolution means how number of bits for each pixel the data is being acquired. If it is say 7 bits, that means the value between 1 to 127, any value can be assigned to a pixel. If it would have been a bit like in earlier versions the panchromatic, we had only the 6-bit data, and therefore it was values were ranging only between 0 to 63. So in case of list 3 it remained 7, but in case of AVHRR, though it has poor spatial, relatively coarser spatial resolution, but the quantization or radiometric resolution was better than other sensors or previous sensors. And spatial coverage was also, spectral coverage was also, here we had 4 channels, but in of course panchromatic will have only 1, and that almost identical in case of list 3 and AVHRR. And this also a number of arrays in this linear sensors were also different depending on the resolutions. If resolution is more, the number of CCDs are going to be much more, whereas if resolution is coarser, these CCDs will be relatively less. So this is how things gets affected with the spatial resolution, the swath bits, the radiometric resolution, and also temporal resolution we see. Here the IRS 1C 1D had a panchromatic camera, IRS P6 has the LIS 4 which was also mono or panchromatic. Many things are completely comparable, but the major difference became between, like I mentioned earlier, that in case of IRS 1C 1D we had only the 6-bit data. That means pixel value could vary only between 0 to 63, total number 64, whereas in case of LIS 4 we had the 7-bit. So the this radiometric resolution was better in case of LIS 4 which was on board IRS P6, and a spectral coverage was position at different location, and number of CCDs in case of PAN we had 3 arrays, whereas in case of only single array data, because by that time people realized that it is single array would be more than sufficient. As you once the spatial resolution improves, then the clarity of an image also gets improved, and this is what the example is, that if you are looking a city, you can see all individual roads, and if you zoom it to a certain extent, then you will be able to see individual buildings, of course from the top. So this is a example of Milan city of Italy. You are having our own IRS LIS 4 data, 5.8 meter resolution, 7-bit radiometric resolution, and the coverage here it is having about 70 kilometer, and the channel which is being used red band, whereas this is false color composite, and this is IRS LIS 4, IRS P6 LIS 4 sensor, and the resolution again here is 5.8 meter resolution because it's a merged scene, 7-bit and 70 kilometer. So you can see the clarity in this image relatively, because this is the merged image of Palm Island of Dubai, which is a completely man-made structure in the sea. Also, as a spectral resolution improves, and if a swath is much more, you can cover large areas. One example of Mansarovar Lake is given here, and also part of Myanmar coast is also. So this is AVHRR's data, and this is a LIS 3. LIS 3 sensors, as mentioned earlier, became very popular because the spatial resolution 23.5 meter was quite good at that time. Even still it is quite good because it provides the relatively wider swath, which becomes very useful for several kinds of studies. Now the new in the series is the Cartosat, which was only launched on June 2016 this year. The spatial resolution has improved very significantly. It is now only 0.65 meter, that means 65 centimeter, and as I have been mentioning that higher the spatial resolution, lesser the swath width. So swath width has reduced to about now 10 kilometer. So only a very tiny strip, a very narrow strip of the part of the earth is being covered, and of course the band also has become narrow, but see the quantization. Instead of now having 6 or 7 in panchromatic, now we are having 10 bits data, and it is a huge improvements in case of spatial resolution, in case of radiometric resolution, and it is having the roll tilt capabilities of about 26 degree. So it can acquire the stereo data, and stereo data can be used to prepare very high spatial resolution, roughly 65 centimeter spatial resolution digital elevation model of any part of the globe. That is going to be a great boost in the Indian remote sensing missions and for world as a whole. As India has got long plans, and it is working on that. On this chart only few examples are shown. The latest one, as I have just mentioned, is Resourcesat is there. It will continue to provide the data. Then of course our radar remote sensing satellite Risat is also there. It is providing the data. Then there are OceanSat, which was again radar set but mainly focused for oceanography related applications. Cartosat 2, which worked up to 2013, and it provided data at less than 1 meter resolution and 9.6 meter swath and 10 bits quantization and so on and so forth. So as you must have realized that if we compare just like in case of Landsat 1 and Landsat 8, same way if we compare IRS 1A and our now Resourcesat 2, a lot of improvements have happened in Indian remote sensing satellite missions, and which are still continuing. Things are improving. Instead of having just multispectral channels or panchromatic channels, now we are changing, and also we are having a radar satellite as well as satellite specifically for preparing digital elevation model or providing stereo data plus our normal multispectral data. Future is also there is for the hyperspectral, that will be in future. That means the more number of channels within the same atmospheric windows we will have. So narrow channels, but number of channels are going to be more, many more. So the spectral resolution is going to improve significantly. Now this is another very popular series of satellites, still operational, still providing data. So we started with this Taros N series that later on it was renamed as NOAA, and NOAA 6 and NOAA 18, even 19 are operational. 18 and 19 is still providing the data, and which covers though relatively spatial resolution. The sensor is advanced very high space radiometer, this AVHRR, that means advanced very high resolution radiometer. This AVHRR sensor is still very popular, though it provides data at 1.1 kilometer spatial resolution, but the swath or the footprint of this sensor is very wide, about 2800 kilometer. So it covers a very large area in one go. Now if we look at the future of say specifically for NOAA, and now NOAA after this 18 and 19, they are going to shift from that, and maybe now it is going to be first METOP satellite has been launched, then METOP 2, METOP 3, these have been also planned. So this NOAA series is going to be replaced by these METOP satellites. Some other changes are also happening in case of GOES and other satellite, but this slide was mainly to tell about the future of NOAA, because there were a few years back there were one survey of applications of remote sensing data, that means the which satellite data has been used maximum, and this survey was done of 25 years of publications of International Journal of Remote Sensing, and they found that NOAA AVHRR data has been used maximum in their publications. So because of free availability of data covering a wide swath, availability of thermal channels, and this data became very popular to cover any large part of the earth. This NOAA data is still being acquired, as I mentioned. It is having 5 channels, and you know that there are visible channel, near infrared channel, and thermal infrared channels are there. All are having a spatial resolution of 1.1 kilometer at the center of the scene. Because the swath is very wide, it's 2800 kilometers, so on the edges the resolution further deteriorate, but because of large swath and because of availability of thermal channels on daily basis or multiple times in a day, the new types of applications have been developed based on just on NOAA AVHRR data. And this is the station which I have already shown in previous lectures, and we have been operating this earth station since October 24th 2002. Still it is operational. It has acquired thousands of NOAA images which we have archived and can be used for long term applications. One more thing which I want to bring here about several times I have mentioned about ground stations. So, we also called satellite earth station. That means that we need to have a antenna system, that is the tracking antenna and or rotating antenna, and it covers a very large area. That means anywhere the satellite, when it is overpassing, especially the example here is the NOAA, then within this circle which is about 3000 kilometer radius, then we can acquire the data, or this earth station can acquire data almost fully automatically. So, this is because it is a computer based system, there is a prediction program about the overpasses. So, once the data is supposed, or once the satellite is supposed to fly over within this circle, and this antenna will go in that direction, will acquire the data, because remote sensing not only involves the analysis, interpretation and application of satellite based remote sensing data, but also how data is acquired. So, for that purpose I wanted to discuss this point here also. Once you are having a large swath width, instead of having just 9.6 kilometer swath width as in case of Cartosat 2, here the swath width is 2800 kilometer, and the advantage is in one go you can see the cloud conditions of entire Himalaya. If there is a fog belt or something, then entire thing can be seen, like here the one fog belt. If the swath width have been very narrow, then you would know that particular phenomena only for a narrow part of the earth. But if swath width is larger, you know a complete extent of sometimes of a phenomena, like here the fog is being shown. Same with the clouds, and these the relatively coarser spatial resolution data are very useful to cover a large area and to monitor things for a large part of the earth. And this is again these are the visible channels. So, a false color composite here, which I have already discussed. This is the thermal channel, which is something like X-rays of and it shows the emissivity. So, that these are all passive data, but the details are altogether different, though in case of NOAA AVHRR the spatial resolutions are same, but in case of Landsat 8 the spatial resolution between visible channels and thermal channels are different. One last point in this one is the Sentinel, which is has become very popular, a radar remote sensing satellite, which is active remote sensing, and Sentinel-1 is a 2 satellite constellation with the prime objective is to cover the land and ocean monitoring or part, and especially because it is providing data for interferometry. It operates in the C-band, and synthetic aperture radar is continuously providing the data, and basically it is a continuation of ERS series of satellites and NVSat. So, now ERS and NVSat are no more in operation, but Sentinel-1 has replaced them, is better satellite, having better sensors and providing regular data including for these interferometry. So, C-band is obtaining night imagery because it is a radar data, so it can acquire data any time of the day. And the best example recently we have observed about from the Sentinel is about using this SAR interferometry capability, or in short we say in SAR, in case of ground deformation studies induced by an earthquake, which has been seen in case of Nepal. This example is from another radar remote sensing satellite of Japan, which is ALOS. The sensor was pulsar, and this ground deformation map, which is the fringes, different colored fringes which you are seeing, can so that the ground information induced by those 2 earthquakes of Nepal occurred in 2015 could be estimated very easily, very accurately in case of such natural disaster. So, this brings to the end of this presentation. Thank you very much.